And I'm going to spend some time now showing you Specutils. So this is switching gears a bit to be more code-oriented rather than UI and visualization tool-oriented. But as Robel pointed out at the beginning here, a major part of this workflow is that we want to enable you to mix and match those sort of workflows, right? The whole reason why you've been seeing all this stuff in a notebook is that you can run the UI from the notebook while at the same time thinking about how to intermix that with more code-oriented workflows. So I'm going to show mostly those code-oriented workflows now, in particular the Specutils, the Specutils Python package. And I should mention, this is also, as a couple people have said now, this is also the package that sort of underlies the science content of all the Viz tool stuff you were talking about, like the line fitting and all that stuff. So pretty much everything you see there, you can access the underpinnings of it by using Specutils the way I'm about to show here. I should also say, since the time is limited, I'm not going to be telling you everything that's in Specutils, but what I am going to do is point out that the Specutils documentation right here has the exhaustive list of all the functionality. So what I'm instead planning to do is work through sort of some of the high-level concepts that are important for working with Specutils so that you can understand sort of how you get data into Specutils to work with. And a single example of sort of a fairly simple science use case that you might see. And then the rest of the notebook has a whole bunch of examples of how you use it for more in-depth science use cases. So the idea is I'm going to go through a short example or a couple short examples here, and then on your own time, if you like, you can go and finish the sort of bottom half of the notebook or pick and choose the parts that interest you the most. And you can ask questions in Slack afterwards if you have time and interest, but that's the core idea, is that I'm just going to give you a taste, as it were, and give you a sense of how this works, and then you can find the things that are most interesting for your science workflows on your own time. All right, so with that in mind, I just need to say roughly the scope of Specutils. Let me execute these imports. You'll definitely have to do that if you're following along in the solutions before you get to or if you're typing live for that matter. But having done that, now I can talk about how this fits into a bigger picture. So Specutils is basically the Python package that's part of the AstroPy ecosystem that is meant for what you might call sort of standard or basic, depending on the way you look at it. It's not all basic, but it's all sort of standard and not cutting edge spectroscopic analysis. And the data structures that are meant for representing spectra in astronomy, essentially. So the Specutils is both of those things, both the sort of basic analysis tools, which is what you're probably most interested in right now, given the name of the webinar, but also the thing you need to carry around in Python to be able to apply those analysis tools to. There's a couple other packages of relevance. So Specviz we already saw. That's part of the visualization tools now. But then Specreduce is a package you might have some interest in if you're interested in doing the reduction side of things. That is not relevant for JWST because the JWST pipeline is going to do your reduction for you, and there's a mission-specific pipeline. But if you're thinking about using these tools in a broader context, you might have interest in that, which also has a selection of tools for sort of reduction as opposed to analysis. All right, but I'm not going to talk about Specreduce anymore. Now, everything, or Specviz, the rest is all about Specutils. So I'm going to start by talking about these core data objects, because that's really fundamental to working with the spectra, really, in any of these tools, is knowing how they're stored. So the most important one is this object called Spectrum1D, which is the closest thing to what you probably have in your head as a spectrum. At its core, it's basically a spectral axis, which can be wavelength, frequency, energy, whatever. In our example case, it's wavelength. Can be just as an array, as in this example. And then there's another attribute called flux, which is, the y-axis of the spectrum. It's called flux, partly because that's 4 characters, easy to type, but also because, it sometimes is physically flux. It is not always or restricted to be physically flux. It could be, photon counts. It can even be, raw detector counts, essentially. The code doesn't restrict that, despite the name being flux, but it's a sort of shorthand to mean the y-axis of the spectrum. The other thing Spectrum 1D objects can carry is WCS. That's a sort of functional or analytic way of representing the spectral axis. And then metadata, which means, like the header keywords, essentially, if you're loading from a FITS file. And also uncertainties, which I probably won't have time to go into in too much detail, but they exist, and you can go back to the solutions and this notebook later if you want to know more about that. The other thing I want to highlight about Spectrum 1D that might be a little confusing is that despite the name ending in 1D, the flux does not have to be 1D. Right? This same data structure is used in some places, for example, in Cubeviz to represent data cubes, because the flux can be many-dimensional. It's only the spectral axis that is required to be one-dimensional in this object. So it's for anything that's like rectified, where they all have the same, many spaxels that all have the exact same set of wavelengths, let's say. If you don't have that, if it's a, fiber spectrograph, let's say, where they all have slightly different wavelength solutions, there's this thing called spectrum collection, where the spectral axis is instead matched to the flux. I'm mentioning that exists because it might be useful for certain science use cases. It's used in some places in the Viz tools, but I don't want to dwell on it right now because it's really more complicated version of Spectrum 1D in some ways, and that's the one that I'm going to use for the rest of this notebook. So it's really the simple case that I'm showing here, but the whole point is that in these more complicated cases, the tools mostly work the same way, or at least are meant to work the same way, and it's a bug if they're not. And in the end, you can sort of use the thing you learned on the simple case to apply to the more complicated cases. All right, so with that in mind, I'm now going to focus on things you can do with and to Spectrum 1D objects. A data file that's the same one we've been looking at for other parts of this webinar. And the simplest way to load something like JWST data where this has already been done for you, essentially, is there is a spectrum1d.read method that you just call on your data set, get out a spectrum. For something like JWST, where there are already functioning readers, this is the way to go. This is going to be a lot easier than sort of doing it by hand. And there's actually a lot of things other than JWST that have functioning readers. So this cell here, I called the help on the reader method. That shows the help, but most importantly includes this table here that lists all of the available readers. You can see some of them are JWST, but some of them are things with actual real data, like HST, several different ground-based data sets, including Sloan and so on, that were all provided by someone, generally at one of the institutions that supports these instruments. So the idea is, if your data you're looking at are one of these sort of things where there's actually a well-defined format that has somebody who is willing to write a reader for it has contributed, then you're all good. But as we know, data sets are often not that simple. Sorry, I think we ran out of time to do this exercise, but if you're interested, the point of this exercise is basically doing what I just said, but on, say, a Sloan galaxy or some other data set you might have on hand. So instead, I'm just going to go on to talking about how you might create a Spectrum 1D object, not using the built-in readers, but by hand, meaning either you don't have a reader if it's some data set that you have, or if it's even something that the readers support, but you want to make a new spectrum because you want to jigger with it somehow, you can. So to give an example of how that works, let's load that file that we were just looking at that we actually used the reader on, just as a FITS file. Looking at that file, it's a pretty simple FITS file that just has a table that has 2 columns. Let's look at those columns. Make sure we understand what we're looking at. The header, okay, it's got one that's called wavelength, one that's called flux in microns and microjanskis. That's good. We knew that because we saw it already, but okay. I can extract file, another variable just for convenience, and then make my spectrum1D object just to spectrum1D, and then flux equals whatever array I think is the flux array. In this case, it's conveniently enough flux. And then you have to provide it with some sort of units, right? In this case, we know it's microjanskis from the table right up here. And conveniently, that's also an AstroPi unit that's already defined, so we don't have to do anything special with that. We just use the standard way of AstroPi provides for providing units. And then the wavelength we provide in basically the exact same way, and it's microns, and that's also a supported unit. All we have to do is that. That gave us an object. Let's have a look at it. What's this? And that's the exact same spectrum. So that's good. Basically, we replicated what the reader did, but with the flexibility that if you wanted to do something, I'm just going to zero out the flux to be silly. No, I have a better example, which is, let's say you knew your something was wrong with your wavelength solution, so you needed to offset it by, a micron. You can do something like that, and now the wavelengths are offset, right? So you can use that to do sort of custom things as you load your data in without relying on the reader to take care of stuff for you. All right, so I did a few things there that you might not be super familiar with, so let me take a second to back up and talk a little bit about what the spectral axis actually is. So a spectral axis right here is a AstroPi quantity object, which is essentially an array that has an attached unit. This is a NumPy array, which is very standard if you're used to thinking in Python, with an associated unit is basically what it amounts to, and machinery to make it look pretty when you printed a notebook is the other thing you're seeing here. The other thing it has, though, because it is aware of its unit, is it lets you do conversions, right? And, for example, if you're like me and you're used to think about ground-based spectra, you probably believe the only unit that was meant to be used for anything is angstroms, and you do that, it does it for you. That might seem silly because it's just a simple multiplicative offset, but what's more useful is the case of something like if you want to convert to frequency. If you want to convert to like some random unit, it's going to give you this unit conversion error because time and space, except for in the relativistic context, time and space are not technically the same units. But if you want to convert to frequency, you need to just tell it, I'm in a spectral context, and then it will do that for you. That's what this u.spectral thingy is saying is, trust me, this is a spectrum. I know, don't freak out. You're okay, computer. And indeed, it does its switch over, and this is now that same spectrum, but in terahertz instead of angstroms. There are some convenient little accessors that do that for you, like JWST spec.frequency. Frequency does that, is basically the exact same thing as what I did up here, only, it's hard-coded to give you gigahertz, so you might have to do that if you really actually wanted terahertz, but it's the same idea. So that's convenient, but is not, right, so that's convenient. It's a different order, speed things up. So the other thing, about unit conversions that's worth thinking about is that, if you're like me, you often are like, f lambda to f nu, which is it again? Where does the nu and where did the lambda go? The same machinery that we're looking at here will take care of that for you. So now this is the flux, not the spectral axis. If I want to convert to f lambda units, it won't work as is because it doesn't know that it's a spectrum. But if I tell it it's a spectral density, you might think that's going to work, but no, because spectral density has to know the spectral axis. Fortunately, we have the spectral axis easily enough. And now that's the proper conversion. So that's fairly convenient using just sort of AstroPi machinery, nothing that Specutils has in it. But Specutils is more convenient for this, mainly because it has, it knows it's a spectrum, right? You don't have to do this added bit here that looks kind of opaque, and you probably aren't going to remember if you're not, 5 minutes from now. But Specutils has this thing, new flux unit, that is named in such a way that hopefully you can see what it is. You ask lambda units, and it just gives you a new spectrum. That's the same spectrum, except with this conversion I just showed you up here, having been applied to it. Example, if we give that a name, plot it up, you will see that indeed it's got that tilt in it that is exactly what it should have if you do a conversion from f nu to f lambda or vice versa. And you didn't have to remember which is the right way. And if you're like me, that's a huge lifesaver. Right. So the other thing to highlight about spectral access and the way these attributes are handled here is that in addition to this sort of array-like approach that I've been showing you, also embedded in these WCS objects, or in these Spectrum 1D objects, is the WCS, the World Coordinate System, which you can think of as just an easy way to do the pixel to world, which in this case, is wavelength conversions. So for something like a pixel 10, that's maybe silly because we already just did stuff like that. But it's really useful if you want a pixel in between other pixels, because it's perfectly happy to interpolate between them in a way that the WCS and the file, most importantly in something like JWST, where there's very complicated WCS information, it's not just like linear interpolation, it's actually the right kind of interpolation. This will also, of course, go the other way. You can ask things like, I want the pixel that corresponds to 1.2 and 1.3 microns. That works just fine. And that gives you pixel numbers that are fractional, just as you'd expect. So that's, I'm running low on time, so I'm definitely going to have to skip uncertainties. I'm going to try to, let's see. I would have normally said things about arithmetic, but I don't think I have time to do that. I want to jump straight to the analysis example. The key point to note here, I guess, is this part, that you can take a spectrum, JWST spec, add or subtract a number that's got units, and it does exactly what you'd expect, right? So if I'm going to do a line analysis like I'm about to do, where I need to subtract the continuum, there's fancy ways to do continuum subtraction that are elsewhere in this notebook. But if I just want to quick by eye subtract the continuum to be about right around, this is the H alpha line, I can literally just subtract 0.5 microjanskis, and I get a new spectrum out that is exactly what you expect. So most notably then, because what I do want to do is measure the centroid of this line, is the simple analysis I wanted to do, sample analysis I wanted to do. You can even do this as long as they're compatible units using other units like nanojanskis, which are a more convenient way to write the continuum in this case. And then I can create a object like this. That's just the spectrum we've been looking at this whole time, minus that continuum level I just defined. I'm going to do some copying and pasting just for time's sake. You'll see, again, this is a spectrum that has its continuum level now right where we want it to be for this line. So now the next thing I need to do is identify where this line is for me to be able to do any centroiding. So I've done that in advance just to speed things up between these values. But you can see later on in the notebook if you want a way to do this in the notebook. An alternative answer is to use Specviz. That's not in this notebook, but you're welcome to do that too, because it's probably much more efficient if you're already willing to use Specviz. Then let's see, what's the next thing I'm doing? Oh yeah, so just to, again, jumping around here because of time, but here's the area I selected. I've zoomed in on the spectrum a little bit now in the H-alpha region. And this is the area I've defined as being where I think the line is. Key is that I use this spectral region object, which just says, here are the two bounds. As you can see, I did it in angstrom because that's where my brain goes. But you can use whatever units you want as long as they're compatible in the sense of being the right physical kind. And after that, all I have to do to compute the centroid is take the spectrum, give the region, and run this function centroid on it, see what it tells me. And it tells me an answer that is a result of doing the sort of standard centroiding calculation on this line, just this region of this line. So that's useful now because I can use, the redshift formula we all probably learned at some point in some class. Just, say the rest wavelength of H alpha is 6563. And bam, now I get an answer for the redshift. And it's done any unit conversions necessary for me, essentially. Right, like it's embedded in here is that it was actually in microns, but it did the conversion when I did -1.